Hi, and welcome to our first part of our derivatives unit. So we're going to be talking about a few things today: average rate of change and instantaneous rate of change. We're going to be looking at a bunch of graphs, and this idea of differentiability is going to be the major topic of this chapter. So you might have seen this before. Well, you have seen this before. This is the slope formula. So what this secant line is we're just looking at the average rate of change. So we've got a curve and we're seeing like, okay, over a chunk of time, what is going on with the slope of this thing? Now, this is a crazy way to write our slope. Really, we're just taking our x and our y values, and then we're putting a small change to our x value. So we originally had c, and we made our x value just a little bit bigger. And then we did our f of x, but our x is just a little bit bigger, is what this thing is trying to represent. So we're looking for the average rate of change of our function over a small interval, so we can get an idea of how this function is changing. So if I've got f of x equals x cubed plus 1, if I wanted to do this average rate of change, I would do the f, I need a pen, f of 3 minus my f of 2, because those are our two y values, y2 minus y1. You've been doing that for forever, over our x2, which is 3, minus our x1, which is 2. We just need to evaluate those things now. So f of 3, if we cube that and add 1, we get 28. I'm just plugging it into my f of x up here. Then 8 plus 1, so that's 2 cubed, is 9, over 3 minus 2, which equals 19 over 1, or really it's just 19. That's all it is. So that is our average rate of change over that interval for our function. And it seems to be going up about 19. What if we look at a different interval for this same function? If we do our f of 1 minus our f of negative 1 over our two x values. So we want 1 minus negative 1. F of 1, we're still going to be putting it into our f of x up here. So 1 cubed plus 1, that's 2. Minus negative 1 cubed, that's negative 1 plus 1, that's 0, over 2, which ends up equaling 1. So we seem to have an average rate of change from negative 1 to 1 of 1, and we have an average rate of change of 19 when we go from 2 to 3. So it seems to be changing much more quickly in this first interval than it was in the second interval. It was only changing by a little bit. It was only changing by about 1. Now we're going to take this and we're going to say, okay, well, we want to figure out what is our instantaneous rate of change. So you can write this down, and I'm going to pause here for a second, and I'm going to bring up a graph so we can kind of show what I'm trying to talk about here. Okay, so we want to figure out how this thing is actually going to work on our graphs. Here is an example of the thing that we were just doing when we were doing our secant line before. So that secant line was looking at when this h value is pretty far away. We were looking at our slope, let's see, when it was like 2 away. There we go. So here we've got about a slope of 1. Our secant line is kind of like going through this point here, but it's not really telling us like what is the slope at this point. If we adjusted it so that it was between 2 and 3, we could see we could get a really big slope. But what we're looking at with that limit is saying, okay, well, as we bring these points closer and closer together for our secant line, what is happening to the slope of this line? What is the slope of our line going to be as that secant line transitions more and more into a tangent line? Tangent line is when it bounces just right off of our graph. It doesn't hit it twice, it only hits it once. Hits it at one point right there. It doesn't hit there and then hit again somewhere over there. We want to be able to just find our instantaneous slope. What is our change? How much is the change happening at just that one spot? So what is happening to our h value or the c value or the delta x, whatever that might be, as that value gets smaller and smaller and gets closer and closer to 0, if we can check that limit will tell us what is the instantaneous change, as opposed to the secant line that we were doing before. This is our secant line from before. It was telling us like an overall rate of change. But look, it's doing all kinds of things in between. Our secant line can't figure it out. But if we checked a bunch of tangent lines, we could talk about how this thing is moving from one spot to another. So that is this instantaneous rate of change. And we call that tangent line, that slope of that tangent line, the derivative of the function. So it's telling us what is the slope of that tangent line at a very specific point on our function. And it tells us sometimes ones for the entire function. So it tells us a whole bunch of places. Now there's one other type of line. So the tangent line just bounces off real quick, but just so we can play a little bit more with this idea of slope, there's also a normal line. A normal line is perpendicular to the tangent line. So it's just like, okay, well, that's our slope right there. But if we wanted to make a perpendicular line at that point, which you need kind of like two lines to make a perpendicular. But if we wanted to be perpendicular to that point, that's what normal is. And that's that normal line that we're creating. So let's kind of play around with this a little bit. All right, so we're going to test out this derivative thing on this function. We're going to use just regular x cubed instead of x cubed plus 1, unlike our original one. We're looking for tangent and normal. So for our tangent line, we're going to do f prime of 1. A little tick mark means prime. We want to do the limit as delta x approaches 0 of f of, and the x that we're using in this case is 1, keep the plus delta x, minus f of 1. So we're replacing all of the x's with 1s. We're keeping the delta x because that's representing our small amount of change that we want to do to that x value. We just want to nudge that thing over to 0. Minus 1. Okay. All right, so in our numerator, we want to use her f of x function. So the limit as delta x approaches 0. We want to replace the x with 1 plus delta x. And our original function is that x cubed. So we got to do 1 plus delta x cubed. For f of 1, you just put a 1 in there. So that's just 1 cubed. I'm going to clean up that denominator a little bit. We've got 1 plus delta x minus a 1. So this 1 and that 1 zero each other out. Those two things are just sort of gone. 1 minus 1, that's 0. So all that's left in our denominator is delta x. You might see a lot of functions, a lot of times when people write this, they actually don't write the x and they just put a delta x in the denominator because they do zero out in pretty much all of these. Actually, I think it is all of these. All right. Now, to simplify that numerator, I'm going to use an old trick. I'm going to use Pythagoras, the Pascal's triangle. I don't know if you remember this thing. It's a neat trick for doing binomials to various powers. I'm going to zoom in a little bit. That 1, 3, 3, 1 is what I would use for a cubic. You might recognize the 1, 2, 1 as something you would use if you did a binomial squared. So if we're doing a binomial cubed, we can use the 1, 3, 3, 1 as our coefficients. So I need to do the limit. And this is going to save me a little time. It's not going to save me a ton of time, but it'll save me some. So we got 1, 3, 3, 1. Then we want to do a descending order with our first term. So that's 1 cubed times 1 squared times a regular 1. And then an ascending count with our delta x. So I'm going to start with none. The first one's going to have, the second one, I'm sorry, will have just a regular delta x. Then we'll do delta x squared. And then we'll end with just a delta x cubed. All these get pluses in between them. There's a goofy thing that happens with plus or minuses. if you have other ones, but fortunately we don't have that. Finally, I still got that -1 cubed, so that's -1, right, -1. And we're still all over delta x. All right, so let's clean up that numerator because it is a right mess. So the limit as delta x approaches 0, we've got 1, that's 1 times 1 cubed, plus 3 times 1 cubed, 1 squared, so that's 3 delta x, plus 3 delta x squared, plus 1 delta x cubed, -1, all over delta x. Well, our ones seem to zero out again. This one and that one, those two zero out. So we're left with just delta x cubed. I'm going to put them in a nice order. 3 delta x squared plus 3 delta x. All over delta x. Ooh, now we can divide that delta x out so that it'll be gone. So we're left with just delta x squared plus 3 delta x. Sorry, my brain kind of stopped for a second there. Plus 3. And this is still a limit. Sorry, I forgot that. So plug in your limit and we get 0 plus 0 plus 3. So the slope of the tangent line when the slope of the tangent line when x is 1 should be 3. That is the slope of our tangent line. If we want to find the slope of our normal line, you just do the opposite reciprocal of that. So flip it upside down and make it negative. So negative 1/3. We can plug those into point slope form. We're using the point 1, 1 from up above. So y minus 1 equals 3x minus 1. Y minus 1 equals negative 1/3 x minus 1. If we wanted to be fancy, we have our equations like they asked us, but if we wanted to put them in, I don't know, slope-intercept form or something, we get y equals, let's see, that's 3x minus 3x, but then we got to add the 1 from over there, so it's going to be -2. On the other one, we get y equals negative 1/3 x, so that's positive 1/3 plus a 1, so that's plus 4/3. All set. Now we can even test this out using that other thing that I was using earlier. We could take a look at, okay, well here, I'm just gonna make this different for a sec. Here's our point of 1, and we wanna figure out what our tangent line is going to be. So right now the slope seems to be, let's see, we're at like 1, 2, 3, 4. So we got about a slope of 4. But as this thing gets closer and closer to 0, boop, now this is a tangent line, so it just tinks right off. It's got a slope of, let's see, well, it's got a point right here-ish. Yeah, point right here. And we got a slope of 1, 2, 3 over 1. So we got a slope of 3. And look, it's going through -2. So sweet. We could write the secant line if we wanted to as well. It would be y equals negative 1/3 x plus 4/3. So this line is secant, so it's perpendicular to that tangent line. No, it's normal. It's not secant. It's normal to that tangent line. So that is our perpendicular normal line. This one, as blinky. But the other line is the slope of our tangent line, which is pretty ace. Oh, it even tells me my slope right there. Isn't that nice? Cool. Oh, no, that's how big it can go. It can go up to 3. Sweet. Problem done. That was a lot. All right, what's next? The next thing is differentiability.